Alright, in this video I'm going to be discussing the equation of motion for a coupled oscillator. We have two masses, mass 1 and mass 2, and 3 springs. And each of these springs has an independent spring constant and an independent natural length. Okay, and some topics we're going to discuss, just definitions, the parameters of the system. We're going to define an equation for the length of the spring and then use that to define the equation of motions for mass 1 and mass 2. Okay, so these dark boxes right here on the out, these two outer ones right here are fixed, and then these lighter ones are free to move. Okay, like I said, big L is the actual length of the spring at a given moment. So this is a variable. Little l is a constant, just describing the natural length. Okay. So x1 and x2 are the distances, or the displacement from the equilibrium point, not the location along this axis, but about this point and about that point. Okay, so we got L1, big L1 is this is just the natural length plus the displacement. If you go farther to the right, the spring's longer. Farther to the left, spring's shorter. Okay. And then for all these, we did the change in length, which is just the final minus the initial, and it's just x1. For x2, you have, for L2, you have again the original position, or the original natural length, but then as x2, right here, as x2 grows, you can imagine the spring will grow, but as x1 grow, or as x2, or as x1 moves to the right, or increases, I should say, this spring becomes smaller. So for that, we have a negative x1. You could just work that out. As it becomes more negative, negative times negative positive, this becomes larger. And then same thing, subtract the original natural length, we have x2 minus x1, and the same process goes for L3. And again, this is negative because as this increases, the spring becomes smaller, so we put the negative. So this gives us the change in the spring with respect to the natural length, and from our normal spring force situation, that would give us the magnitude. It's a restoring force, it's opposing, but in this case we have to test initial conditions to help find out the direction of the force. Okay, so we're going to go through each case and just use initial conditions using displacement to figure the direction of the force. So for spring 1, this is just your normal spring situation. As the spring increases, or the mass moves to the right, it pulls back to the left. But then we also have a force here from K2. Okay, using the displacements from L2, we use that same equation, but now we have to figure out the direction of the force. Okay, so holding, let's do x1 can move. Okay, so x2 is 0. As x1 increases, there'll be a force. So as x1 increases, a force pulling back. But for x2 increasing, it would be stretched versus compressed, and then it would also pull back in this direction. So I've put a plus sign here. And then just expand these terms out to individual terms. I recombine them in terms of x1 and x2. Doing the same thing for the mass 2. I just hold, well, in this case I don't need to, as x1 increases, you could see that the force from the second spring would push the mass 2 to the left. And for the second spring right here, as mass 2 increases, I'm sorry, I should have been looking up here first. Yeah. So again, as x2, we just do the same process. You hold x1 constant, move x1, and then vice versa. And you'll see that we have to include a negative term in this equation so that the forces match, or the signs match the direction that the spring will push. If it's based off if it's a stretch or a compression. And then same thing, I've expanded the terms out and then recombine them in terms of x1 and x2. And so this is the completed equation of motion for this coupled oscillator system.